My name is TJ Rodgers. Up until about a year ago, I was the founding CEO and CEO of Cypress Semiconductor Corporation, so I'm a chip guy. Now I'm with Waterbit, so I'm a dirt guy. And I got to tell you that I find soil and agriculture an extremely interesting thing, and it is very high tech, and it can benefit a lot even more from high tech. So that's what my talk is about today. So if you're not an electrical engineer and I start talking about complex dielectric constants, just sort of cruise for a couple minutes and I'll come back to something you'll recognize within a few minutes. Okay, today I'm going to talk about using technology to water with and what that can do for you, and I'll show you actual results. And in my case, I own 3 vineyards, and I've always been interested in this for a decade, actually, and we've actually got some things in our vineyards to demonstrate, and I have a demo up here. Water in soil is measured by a thing called volumetric water content, or VWC. And it's simply the volume of water per liter per volume of soil. So for example, if you take a half a liter of water and put it in a liter of soil, you dump in a half liter into soil, the soil won't get bigger, and you then have 1 liter of water with 50% volumetric water content. So it's a pretty simple measurement. To bring it to home, 1 inch of rain creates 8.3% volumetric water content increase on a foot of soil. And that's the measurement. This is the device that people have used to measure volumetric water content. It's from a startup in Napa. It's called a VWC Sensor, or volumetric water content. It's a little printed circuit board, cheap. You poke it in the ground, and then it's got some electronics. The electronics looks like it was made by people who live in Napa, and then the wire comes out to give you the data. It burns very little power, it's fast, and it costs $40. Now, of course, if you were in my industry with the sharks that I've lived with all my life, you take this thing apart, which I did, and you would conclude this thing could get made for something like $4 and easily be sold for $10. And I'll talk about that later. They claim it's accurate to 2%, that's BS. Absolute 100% BS. Okay, if you cut across that line there, you find the printed circuit board's got 2 copper wires in it, and these are their dimensions, and then these copper wires, when they're surrounded by dirt, form a capacitor. So basically there's a positive plate of the capacitor coupling with a negative plate, and that's all it does, is it measures capacitance. When the thing's in air, it has a capacitance associated with air. When it's in soil, it has a different, higher capacitance, and that is the ratio of what's called the dielectric constant of soil divided by the dielectric constant of air. In effect, the ability to make a capacitor. And I'll talk about that in a minute. So when you stuff this in the ground, it can measure the dirt's capacitance, and that can relate to water pretty accurately, actually. Here's an example. Air has a dielectric constant of 1. So this little capacitor here, if you measure it, has a capacitance of about 5 picofarads. Dry soil is a dielectric constant of 4, moist soil 6, wet soil 18, and saturated soil 70. So basically this 5-puff capacitor, 5 picofarad capacitor in air goes all the way up to 390 picofarads or 350 picofarads when you put it in wet soil. So there's your signal. You poke it in, measure the picofarads, and it tells you how much water is there. There are 2 companies that make these things, Centec in Australia and AgTech in South Africa. I have also filleted all of their products in my quest to find out how they do it and how we can do it better. Here's an experiment. This is done by a student at UC Davis. I work with them. He cut a post hole in the ground, and he stuck one of these things in sideways at 3 different depths. And then over a period of 18 hours during one morning and afternoon, he dumped some water down the side of the post hole, and here's the signal you get. So this is the 3-inch one. You see the water during the day drying down a little bit. Then there's the water dump. Then it went up, and then overnight, nothing went out of the hole because it was dark and water wasn't evaporating. So this is a typical signal you get from a water probe, volumetric water probe. Here's the one where I said if you don't get this one, you cruise, and we'll be back to normal human stuff in a few minutes. This is a graph showing what's called the permittivity, which is in effect the dielectric constant factor relative to air. So dry soil is 4 times air, and therefore the capacitor would be 4 times higher. And then this shows various kinds of soil, and you would go in and measure how much your capacitor went up by a factor of 20 and come over here and say, well, the dielectric constant, the volumetric water content is 40%. And this is actually in a percent of saturation. It's not an absolute number. Okay, he then calibrated for sand and clay and mixtures of sand and clay, and the point here is that soil can make a huge difference. And therefore you have to calibrate these things for the soil that you're in. And soil can make a difference by walking 50 feet in one direction. The dielectric constant and therefore the volumetric water content is 4 for pure air, for sand, and 78.4 for pure water. So basically soil, depending upon how wet it is, forms a continuum. Measure the capacitance and infer from that the dielectric constant. Here's their circuit, and what they did was they made soils with various volumetric water contents by taking Miracle-Gro, says right there Miracle-Gro, and putting the right amount of water in it. And then they looked at the output of their circuit and they got this many volts. So this is their calibration curve. The problem with it is that if you have a tiny change in voltage, it leads to a 10% change in volumetric water content apparent measurement. That's not good. So this is a bad circuit. The right circuit to use is what's called an LC oscillator. It's a combination of an inductor and a capacitor, and it has a well-known frequency given by that formula. So bottom line, if you have inductor that you know, then the soil capacitor, whatever it is, will cause the circuit to oscillate at that frequency. There's one more thing to worry about, and this is where another point about cruise for a minute. There's the permittivity, which is the dielectric constant increase, and then there's a thing called imaginary permittivity, which only a physicist would say, and this actually came from a physics paper out of Dartmouth College. And it just says the soil capacitor has a parallel resistor with it. So you have to measure both the capacitor, which is this graph, and the resistor, which is this graph. And the resistor can screw up the capacitor measurement. So you want that resistor to be as high as possible so it, in effect, disappears. Okay, this is the capacitance versus frequency, and you see that it changes, and this is because the ions in dirt can move, and you have to get up to at least 50 megahertz of frequency, we're talking radio here, in order to get the capacitance curves to be flat. And this number is actually reciprocal resistance. You want to drive it down as far as you can, otherwise it will interfere with the measurement, and that says 50 to 100 megahertz. So the point here is that you have to measure at high frequency, and I'm talking RF here. So there's your oscillator, there's your parasitic resistor, and there's your frequency. And we started to set out to make a really cheap one of these that we eventually could sell in high volume to people in agriculture. By the way, because what I'm saying sounds techy, especially if you don't deal with electrical engineers, you should not infer this is flake tech. The company I worked for ships about $600 million a year to automotive. So your BMW dashboard, your Toyota dashboard, the engine controller in other cars comes from electronics. So this electronics is complex, but it can be very reliable and very inexpensive both. That's why electronics is in everything today. So here's my drawings. This is my Saturday morning scribble. And the electrode ends up looking like this. So you got low-cost PVC pipe, stainless steel rings. We do the geometries. There's some E&M stuff you do to figure out how big they need to be. And the capacitor is basically a donut-shaped thing going from one ring to another. And the thing is 8 inches long. We call this thing a firecracker because it kind of looks like it. Here's one here. There's the electronics inside. So there's the inductor, there's the capacitor, which changes with the dirt that's wrapped around it, and a bunch of other stuff. Then there's a cord that runs through it like that, and you basically plug them one end to the other to make your device. Now, I promised the people I work with that I wouldn't tell you that the processor on here that is made by Cypress Semiconductor costs 35 cents. And because, of course, that sets the price. I just want to point out that the rest of the junk on the board costs 16 bucks, and it should cost about 16 cents. So before this stuff gets really cheap, like all electronics gets really cheap, we're going to have to put this thing on a chip. And unfortunately, one of our guys, the big guy over there, designed a Cypress Semiconductor, and as soon as it's worth about $1 million to us, we will put all this stuff on a chip. So let me show you this stuff and demonstrate it. Kind of interesting. So here's a firecracker. And what I did, of course, you can't hear a megahertz. Your dog can't even hear a megahertz, 100 megahertz rather. So I divided the frequency down by 256,000 so it's audible. And now this is the radio, so that means the waves are going out where the soil would be. So it's measuring my hand right now. So there's an oscillator that's oscillating based on the capacitance between the two electrodes. And if I put it in dirt, which I'm doing now, it's a new frequency. By the way, a frequency is like a clock. I can count it, right? Tick, 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 and then you count the number of ticks in a given time. Here's water, which is equivalent to the wettest possible dirt. So there's a big signal. It's easy for people in electronics to measure between those two extremes, and all dirt is between those two extremes. It's a Radio Shack. Okay, so that's the element. Where's the long one? Say again? Okay, so the point is then you take these and you shove them in. This is a hole cut out of another piece of PVC. You put them in the PVC and you stack them in. And so you have one at 8 inches, one at 16. So this would have 6 sensors, every 6 inches for 48 inches. Today, these probes cost about $1,500. I heard a guy earlier talking about how he, put one out in 10 acres and see how it works. So I have the probes per acre being 0.1, meaning none of you, if you're smart anyway, would do anything other than do an experiment on 10 acres and see if it worked or not and get comfortable with it. Waterbit's going to bring out a probe for $1,150. And at that point, I'll show you why I believe that. It would justify putting one every acre if you wanted to control acre subplots of a farm. But really the exciting thing for me here is the future when this thing's going to be 20 bucks. After we've made that chip, after the probe is cheap, throwaway cheap, you just buy it and use it. Then you can start talking about putting in 10 probes per acre. And all of a sudden, you can have a three-dimensional picture at 6 different depths, what your water looks like. The computer can understand that. It can look at it every 15 minutes, and it can calculate how to water. And then things will change for you, and I'm not just talking Buck Rodgers space stuff. I'll show you some actual examples today. This is my first vineyard. That's a toy vineyard, 1 acre in front of my house. This is a probe that's in the vineyard. It was installed on April 15th, and this is 1 year's worth of data from April 15th. So the curves are at 8 inches, and every 8 inches down to 48 inches. This is the day they installed it. The probe was calibrated at the factory in air to be, this is a percent scale, goes from 0 to 100. What I erased here is the engineers said percent relative to what we don't know. Actually, it was written there by the company that sold us this, AgTech. But the point is, once you know the driest and wettest, you know what you need to know how wet your soil is. So when it was first turned on before it was put in the ground, it read 5, and that was where it was calibrated. It then was calibrated at 95 at the factory in water. So that's it. This is the highest number you can get, pure water. This is the lowest number you can get, pure air, and all the dirt measurements are in the middle. And here we have the driest winter in my lifetime in California history, unless there was some worse time in the 70s. Okay, when they installed it with a slurry method. They drilled a hole, they took the mud out of the hole, they mixed it with water to make like slurry, Then they put it back in the hole and they shoved the thing in, and the slurry filled up every crack and tightly coupled the probe to the ground. So there's super wet, super dry, okay? We're in May here. We had another rainstorm, then we had the drying season that precedes having to water the grapes. And as you can see, the deep stuff doesn't get dry that fast. The shallow stuff, 8 and 16 inches, gets dried very fast. There's the watering. Every spike shows when we turned on the dripper system, which dripped right on top of this probe. When we turned on the dripper system, it wet it, and then within a week to 2 weeks, it dried back out again, triggering another probe. After harvest, we didn't water. The driest we saw was 42%. Notice that the deep stuff never got really dry. Then we had this really wonderful wet winter year before this year. You can see the ground saturating up at a 90%, and you can see the top ground, the 8 and 16 inch ground. So there's a picture of a whole piece of land for a year. And it's very accurate. This is really 1% accurate stuff. So, can I trust this to autonomously water my vineyard? You know, I'll automate. I'll just turn it on and say go. No way in hell, of course, would I ever trust my grapes to a bunch of stuff like this until it's proven. So as a farmer/electrical engineer, I had to prove that our watering system would work. Now, we water by leaf water potential. Those of you that know grapes know what that is. You take a leaf at midday, you put it in a pressure bomb, you pressurize it with nitrogen, and you look at the end of the stem of the leaf, and when liquid comes out of it, that pressure tells you what the leaf water potential, or in effect the water status of the plant is. And that number varies. A bar is a metric unit of pressure. A bar is about 15 psi. From 90 to 200 psi. For heavily watered vines, doesn't take that much pressure to push water out of them. To vines that are about to wilt takes more than double the pressure. And then finally hit the permanent wilting point where the water would rather be in the ground than in the grape, and the grapes will die. Okay, I'll say why in a minute, but we don't water till minus 12.5, so we're right on the edge of temporary wilting, and that's a very high water stress condition that produces better quality grapes. That's well known. And then we put on 2 gallons per vine. I'll talk about both of those parameters, when to water and how much to water, because they both can be determined according to what you want to optimize what you're after, and those determinations are different. So, this now is the watering sequence, exactly what I showed you before, but what I've shown here in the black dots is the actual leaf water potential. So my wife, who runs the vineyard, she would measure it, and she's pretty good at this, and the data's pretty stable, and we watered. So here, for example, you see a watering just after a 13.4 reading. You see the spike up, and then you see it coming down. The time for it to come down is about 1 click here, and this is about a week. So we've got a week to 10 days. This one was 2 weeks here between watering, so that's pretty typical. I'd like to talk about some detail, because this is where, if you have this data, understand it, and hook up a computer, you can get insight to your plants way better than, I believe boots on the ground are the best fertilizer, the old statement about vineyards, but there's more data here. Okay, you notice the staircase function here? The thing goes down and then down for these two curves. That's not because I have low resolution on this graph. This graph provides data every 15 minutes, day and night. That's because during the nighttime, this is the nighttime, right where that flat spot is, there's no transpiration, so no water use. Then you wake up the next day and bam, the water gets used a lot, quickly. Then there's another night and another day. So these are, now I know what my problem is, Control A. You see water getting used. Now when a lot of water gets used in a day, your plant's happy. It's metabolizing, it's creating the product. Now when you get down below 60 relative percent on this scale, you notice the steps get smaller. They get tiny down here, and all that says is this plant's not happy, it's stressed out after 60. So you might decide that you're never going to let it go below 60 and tell your computer to do that for you, and that's not that hard. I'll show you. Also, if you notice up here, the steps are kind of small on some of these curves, and you ask, well, gee, the steps are small when there's too little water, and they're small when there's too much water. Why is that? Well, the answer is the plant doesn't like to be waterlogged either. It likes the right amount of water. So there's a sweet spot in here, right about in here, and you can control that because you know when your plants are at it. By the way, here's the close-up of watering event number 1. So you see, this is before watering, you see the watering event, you see the over time drying out over the next, these are hours, so this is a 4-hour scale here. You can see a lot of water went down deep, and that's wasted water. So that tells me here, and we'll do it this year, water more often with less water. Which, of course, if you're paying for it with manual labor, you can't do that, but if the computer does it, it doesn't really care if it's watering every 8 minutes. Bordeaux. Quality rating. 15 is okay, 10 sucks, 20 is great, 18 to 20 are the big years. Okay, this is a water deficit stress index during the critical time variation of the harvest. Dry, wet. Interestingly enough, all the great years had low water. That is, they were below 0.6 on the dry side. Second point, during the wet years, during the bad years, they're all wet. And everybody in Bordeaux at least knows this, that basically they're not allowed to water their grapes. They don't have irrigation, and they get too much summer rain. It dilutes their grapes. And it's well known, Davis led this thing, that water stress makes better wine. It increases the anthocyanin or color, the tannin, and reduces the malic acid, all of which are good for the end product wine. And Bordeaux has to talk about years because they have too much rain, and that's why they don't water. It's not because they're noble or do it organically or anything like that. They get too much water as it is, and adding more wouldn't be very smart. By the way, here's another thing you get. This is temperature. Summer, fall, winter. Notice on the top, the temperature is very erratic, and you can see the days whipping it up and down. And when you get down to 48 inches, you can see it. You can see when the temperature of the ground varies relative to the solar phases. By the way, bud break is a big deal for vintners. Bud break and flowering are very dependent on this graph, and you can get much better information. Okay, here's the vineyard in the fall. The leaves are starting to drop. This is the little vineyard near my house, and these are 1/6 sub-blocks. I have a 1-acre vineyard there, and it's divided in 6 parts. Notice these are behind their head, they're falling, leaf falling, these are less. Well, this is rootstock Riparia gloire, and this is rootstock 420A. Point 1. Different plants are different, even grapes that are nominally identical, and you want to water them differently. So what do? You stick a water, these are experimental ones. The ones, I'll show you the production ones in a while. They're much sleeker, but here I wanted to be able to look at stuff. You measure the water where you want to control the water. In this case, we ran a wire over to the valve because we didn't have RF working at that time. You'll see it work here this afternoon. Run a wire over to the valve, and this little 1/6 acre valve, it's an electronic valve, turns on, runs and does the block. So you can program this thing to turn on and off whenever you want. I'll show you some curves in a minute. In the production side, this would be the riser that has the valve in it. So the water comes up. There would be a flow meter here that measured water, and the computer would keep track of cumulative water for you. There would be a pressure meter up here, so you'd know that you had pressure. You'd get a warning from the machine if the flow was wrong or the pressure was wrong. Here's your radio. This is what turns it on and off. There is no power. There are no wires. This wire from the valve would actually hook to a power supply. That's the solar cell. It just supplies the power for the valve. How, you say, can a tiny little thing like that supply power to a great big thing like that? And the answer is, this is a NetFM valve. It's a state-of-the-art valve. It's a latching valve. And it means you only supply energy to turn it on or off. So it's like a light switch. You flip it on, you don't have to stand there and hold it and flip it off. Most valves today, 95%, you have to run continuous power. You have to have copper lines running for miles. It's 1940s technology. This is widely available now. Another thing that happens, you get weak areas. So there's my always weak, always screws me, never yields right area down in the bottom block. And by the way, I found out what it was. I have 8 inches of topsoil followed by a layer of sand. So when I put on my water, it goes through my topsoil, my sand, and goes away, and my grapes never get it. I just dump it into the aquifer. So I'll change my strategy for that block. How do I do that? Point here, every block or microblock is different. Here's the soil structure report. Those of you in the grape or other businesses know what it is, but this RD stands for root density. These sites are less than 100 meters apart. They're right next to each other in the same vineyard. Here the root density goes down to 12 inches in light brown clay. Here the root density goes down to 32 inches in dark brown clay. And here the root density goes down to 37 inches in gravelly sandy loam, and these things are a stone's throw apart. So that's why you get these variations. The biggest one is the soil composition, both in chemistry and the physical nature of the soil. So how do you control a tiny, tiny little area? Well, that's this one. So there's my flow controller, there's my pressure controller, my power supply, my radio, and there's a valve. And I won't tell you because I promised my guys not to tell you where that valve comes from and what it costs. But it's pretty cool if I did tell you. And then that valve turns on a row, and that valve can run 588 emitters, so you don't need a great big valve there, and that's 0.32 acres for even dense planting. So that's how you control rows. Here's another vineyard. This vineyard is in very sandy soil. This is up in the mountains, our second vineyard. And when we tried to run minus 12.5, which we did before, we had senescence on the leaves. This vineyard was not happy because the water went right through the sand. So we backed off to 10.5 as our watering point. And the second thing we learned is that we had to water more frequently. So here's the exact same curve I showed for the other vineyard, but in this case you can see nothing ever saturates to 95 ever. The lowest end is about the same, it's about 50, and the watering here is a daily watering of a small amount. And it made a world of difference on that vineyard because you're not pouring the water through the sand down into the ground. It works elsewhere. This is a graph on cotton that I kind of liked, but basically this is a yield graph showing tons per acre, and it's a 4x difference top to bottom. So your land, labor, and fertilizer costs are increasing. Your availability of water, at least here in California, is going down, and underperforming land cuts directly into profit. That's pretty obvious. The little box that I have in my vineyard, this box controls a water sensor. This is a Syntec water sensor, and it's in water. And there's a display. And it gives you, there's 6 readings here across, so it gives you the reading. It also gives you the highest reading that sensor ever saw, the lowest reading the sensor ever saw, and where you are. So there's 2 sensors, the rest of them are up here. There's 2 sensors in water, so you can see we're reading 53 and 50 on those. That's saturation. This is not in percent, it's in volumetric water content, and there's a conversion beyond the scope here. And this whole box, which looks like you'd have to plug it in to make it work, runs on that solar cell right there. It's a little bit bigger than your thumbnail. And it's real happy there. The way you do that is with engineering. So we call this autonomous irrigation system, energy consumption. There's the valve, the Netafim, the Israeli valve, burns 0.48 joules. A joule is a watt second. So a 60-watt light bulb burns 60 joules per second. So joule is energy. And you can see during the daytime the system burns 5.6 joules. So there, let me just point out. There's the microcontroller, burns almost nothing. The valves burn not that much. The little Chinese valve is really good. The water probe is the pig, because Syntec didn't invent their water probes to run off a solar cell, but the solar cell can still run them. Our water probe we're bringing out will burn 1/6 the power, and it will cut the thing down farther. So there's the power you need. There's the power you got. I won't comment on that since it's evident to most everybody in the crowd what exactly that means. It just says when you charge a capacitor of 1.5 farads to 4.35 volts, which is what we can do with a high quality capacitor that has to work for 10 years without ever failing, and you allow it to discharge as far as 2.6 volts and it'll still run the system, it'll provide you 9.1 joules of energy, and you really only have to have that at night. During the day you're swamping the thing out. So we have 50% more energy in our capacitor than we need. The box I showed you keeps track of other things to tell you if it's happy or not. This is the power supply down here. So what do you see? During the day, the power supply pumps up to its full value and it limits itself so it doesn't break the capacitor. Then at night, as the thing is reporting every 15 minutes, it slowly burns power. The cutoff for the power point, by the way, is down here. So this thing never gets close to the cutoff. This tells you when a valve turns on and off. And as you can see, when a valve turns on and off, you burn power and the amount of capacitor charge drops down. So this is a diagnostic. This is your radio signal. The limit for this radio signal is 10. You got to be above 10. So we've got a nice strong radio signal and we've got a nice strong solar system. I love looking at stuff like this. If I were you, I'd never want to see one of these. As a matter of fact, I would consider it to be a failure if I had to look at one of them. So our next deployment will be in the third vineyard, the production vineyard. To scale it, you could park three big rigs side by side in this tunnel right here. There's 3 tunnels, 1, 2, 3 under the ground. The vineyard goes here. And I was pretty proud about this vineyard until I met my friends at Gallo. And this is an experiment they did. Nick DeKuzlian, former professor at Davis, gave me these slides and told me he'd be happy for me to show them to you and brag about them. So Gallo, you're looking at big plants producing a lot of grapes. And what they do with it is they do variable rate drip irrigation. Now that doesn't mean they make the emitters go longer, faster, harder. It means that they turn them on for more or less time depending upon where you are. They worked with IBM to get the computing capability, and they also worked, they don't have it on here, but they also worked with Netafim and the valves. Okay, so this is Gallo. They make a lot of stuff and they're really good at it. I've never been to Gallo that I wasn't impressed. Now, what's interesting is my big production vineyard I just bragged about is the same size as their experiment they did. This is their little plot that they diddled with. And actually, they have 100,000 acres. So this is a tiny, tiny fraction, 0.3%, big as my production. And here's their yield on this plot. But this is 32 acres, so it's non-trivial. And their yield goes from 2 tons per acre to 16 tons per acre. We in the semiconductor industry call it Big Sigma, and Big Sigma is bad. That you know, you got an average, but you really don't want that. And getting this smaller is what the semiconductor and manufacturing is about. So Gallo also knows it's about yield. And they just point out that 40% of their vineyard has below average yield, and they could get 30% more yield out of this vineyard if they could get the bad stuff just up to average. Not up to the top, but just up to average. So they started working on it. They use a satellite. They get free pictures from a satellite. You could get the same free pictures. I don't use it. I'm not recommending using it, but I was kind of impressed. So a pixel from a satellite is like a pixel on a camera, and it's 30 by 30 meters. That means that they take that vineyard I just showed you, and they get little sub-blocks that are 30 by 30 that contain 120 to 250 vines. And their strategy was, I'm going to optimize the watering on every pixel. Every 30 by 30 meters. That's what I've been talking about. And in this case, they were ahead of everybody else, and it cost them a huge amount of money. Yeah, huge. You should see this stuff out in the field. But it didn't matter. They're trying to prove if it worked or not. So the idea is you take your part of your vineyard, this is an actual picture, and you drive it make the red go out. It's like Visine, right? You make the red go away, and they do that by applying more and less water. So here's the same vineyard again. They're applying 28 gallons per vine per week. I'll remind you that I applied 14 gallons per vine per year, and they're applying 28 per vine per week. So they got crop load. This is their pixel picture, and then they use this information to automate their watering. In addition, this is water availability. So this is a graph of green's a lot of water, yellow's not so much. This is the NVDI index you can get. This is the yield map they have, and this is the quality map they have. So basically they put all of these views one on top of the other and analyze what's going on in their field. They did good science. So the net result is they can tell you what matters. I'm not too happy with the purple, light purple, blue, red, and brown slide, but the science was pretty good. So water holding capacity accounts for 46% of the variability in that field. And then soil compaction and how good the soil is, so it's half for water, 1/4 for soil, and then anions and pH, what I could combine as soil chemistry, is the rest. So half is water, half is soil, and half of that half is chemistry, and half of that half is physical soil properties. So the great science. This says if you want a lever, water's the big lever. So they call it precision irrigation. This is the map of their field in 2012. This is the map of their field in 2014, and there you go. They've improved the yield, and that's significant. I think if any of you growing crops could get a 25% increase in the crop, and by the way, use less water while you were doing it, that'd be pretty good, and they've done it. Now the question is, can you make it economic? Can you make it reliable? Can you make it easy to put in and it just works and you don't have to think about it? And the answer is, of course you can. Think about cars. Think about this parking lot. Parking lot's got 500 cars in it. Every one of you expects your car to start tonight. You expect to turn on your radio and listen. You expect your headlights to work. So the fact that you expect it tomorrow, the day after that, and every day for the next year. So if all we have to do is bring to bear automotive quality electronics to this problem that have high temperature and freezing and hot temperatures and that, and we can make the electronics that really will work in an agricultural environment is tough. What's the limit? The single vine watering system. So when I was hyperventilating on one Saturday, I took the box, I put a little probe below it. So that probe had, again, the 6 sensors on it. And then I took the box and there's my emitter and my control line. So there's the box and it's controlling the emitter here. And I said, hell, I can do this on a single vine. I can plug that in to a vine. And then I thought about it. Of course, it could be a single microblock or a single block as well. I thought about it and I go, well, let's see. Today it's $1,200. It'll be $500, let's say, in the future. So I walk up to a guy and say, let's see, your vine, it costs $35. You buy this box for $500 and it'll make your vine 30% more efficient. And the guy does the math and says, you know, why did you walk onto my property? But if this thing could sell for $20, all of a sudden it might matter, especially for trees, for example. Per tree, every tree's happy. So what might that look like? So here I've got, there's my radio and power supply, drops water on the ground. There's the little valve that allows the water to come in. There's the emitter supply. So there you are. You hook up an emitter which controls the flow. You run it through a valve. The ground level's right there, dumps it down so you don't have evaporative loss. And then how do you control that? Well, not with my $1,000 box you've been looking at. You go make one of those. Except you make it right, you put the right circuit in it, you make it reliable. Then all of a sudden you got this thing where the power supply's there, you plug this into the ground, it tells the valve when to turn on, the emitter controls the flow for you, and you're done. You add this and you have precise local control of every single emitter in your vineyard. And what's the step after that? I've been working on the Israelis. Sometimes they listen, sometimes they don't. That thing needs to be in there, and it needs to be tiny. It needs to be micro, like microelectronics. Then all of a sudden, I got one of them, I hook up this to it, and it goes down. And on the top side of this, I have a little solar cell. And I don't need much of a solar cell because now all of a sudden the thing's so small it burns almost no power. Now I have an emitter which knows the wetness down below it, and it can turn on, and it's $10. How many would you like? And they work all the time. And by the way, if they don't work, the computer will tell you row 4, emitter 71 is out. Take it and you throw it away and plug in a new one. It's $10. It's not worth a phone call. That's what the future's going to look like, and I am not smoking dope. So back to the first thing, you got one every 10 acres now. Get used to it, understand it, start understanding those little bumps and notches and those curves, and very soon after that, this thing will get so cheap, you won't be able to afford not to use it. Okay, what has WaterBit done? My field's an engineering thing. They've got valve controllers you can beat up forever with professional valves in it. We're making the probe I already described. What I described to you is a local control loop where the measurement drives the valve locally. Then everybody's got their weather station. You now take these things and this is going to run locally, and it's going to run with rain or shine, power off, doesn't care. But both of these things will report how much water did I use, what's my cum to date. This will report what's my water, 6 different levels, to a radio. It's called a long-range radio, and it's N-to-1, so it hooks up a lot of crap, as much as 500 things. It goes to this big ugly beast. Have you guys got one here?
It's out at the desk.
Say what?
It's at the desk outside.
So there's one outside. This is the gateway that takes all this stuff and shoves it up into the cloud with a cellular system. By the way, these things are expensive, but one of these covers 50,000 acres. It's kind of like a cell phone station, if you want to think about it that way. Once you're in the cloud, then you have your computer up there. You can start doing good computing on the data. The professors at UC Davis, ITK in France, they can start putting algorithms in, and all of a sudden you can get much more sophisticated answers. You can buy a software package from them, and then that downloads, so you can get on your computer like I am right now and look at your stuff, or you can get on your cell phone and you can walk over and turn on a valve. You can walk over to a sensor and say the driest you've been in the last year is 42, the wettest you've been in last year is 95, you're currently at 80. You're happy. I'm not going to turn you on, and neither is the computer. And you can walk around with your cell phone. So the vintner's feet on the ground is the best fertilizer, especially if he or she's got one of those in his hand and can see into the ground with X-ray vision. We have developed a new solar volumetric water content system. It is cheap, accurate, and it requires zero maintenance. We understand that as chip guys. It runs 24/7 on a tiny solar cell. You never have to think about having 100 of these on your acres, and you got to go out with a wheelbarrow full of batteries and replace them. It's the new RF solar latching valves. They have no wires. I actually saw a curve where they talked how big the copper wire had to be to run a wire out to a valve that's a half a mile away. And you're burning a lot of copper laying it in the trenches. Just doesn't make sense. The valves only use energy when they're turning on and off, and they use millijoules, thousandths of a joule. The technology for valves today exists to do single vine up to 7.5 acre blocks. Autonomous irrigation system, the product is the water measurement plus the valves, using LoRa to connect to the cloud, through a gateway to the cellular network and eventually to the internet, to provide mobile apps and PC/tablet human interfaces. Most guys I know out in the field like the tablet more than they like the PC. Vineyard water and quality was improved dramatically, and the water can be reduced by 30% with yield going up at 20%. That already happened, actually 25% at Gallo. Sure. Thank you.